Well, today is the last lecture on eutectic, and I'm going to talk about two important things here. First, I'll talk about the free energy composition diagram for a typical eutectic phase diagram, and secondly, I'll talk about the modification of eutectic, and special emphasis will be on aluminum silicon eutectic. So we know that I have discussed three different types of eutectic phase diagrams, and I'm going to take the most general one to give you how the free energy composition diagram looks like. And this is not the first time I am doing it here. I have done it for the isomorphous system, in which I have shown you that the different free energy diagrams or free energies diagrams of different phases are plotted on a same curve as a function of temperature. So at different temperatures we will draw it and show you. So let me just go to the board and show you how things will happen. And so first I will draw a typical eutectic phase diagram with two terminal solutions. So this is the temperature axis, this is the composition axis, pure B end, pure A end, and typical diagram will look like this. And for your information, this is the liquid, this is the solid alpha, solid beta. These two are the two terminal solutions at A end and B end respectively, and this is alpha plus beta, and this is alpha plus liquid, this is liquid plus beta. So there are three two-phase fields and three single-phase fields. So we are going to draw the free energy composition diagram for this generalized eutectic phase diagram. You can draw it others very easily. And as I show you, the free energy composition diagrams will be like this, the G versus XB curve of the phases present here at different temperatures. So temperatures which we will select are like this. We will select temperature like T1, and this is TA, and then we will select a temperature here T2, this is TE, the eutectic temperature, and we will select a temperature at T3. These are our generalized temperatures, and basically the way I have selected temperature is that this will provide you different kinds of possibilities exist when you draw the free energy composition diagram. So what I mean to say is that at these temperatures I am going to draw a free energy composition diagram and show you that. So what are these free energy composition diagram? Let us restate again. These are actually free energy means give free energy versus composition diagram at different temperatures to show the relative dispositions of different free energy curves. What is that? Suppose at temperature T1, I know that the only phase stable is the liquid, all the composition from starting from pure A to pure B. Now to show that, we need to draw the free energy composition diagram of liquid phase, solid alpha phase, and solid beta phase. And it is very clear, and you probably have understood that because liquid is stable, only liquid is stable at T1 temperature, so the free energy of the liquid will be the minimum. The free energy of other two solid alpha and beta will be above that. So let us draw that. So I will draw the free energy of the liquid first, so which is by solid line. This is free energy of the liquid, and I will draw free energy of the two solid phases alpha and beta. Let me draw it like this. So I will draw by alpha 1 by dotted line, and I will draw beta 1 also will be by a different dotted line. Okay. So this is G alpha and this is G beta. Right. So you can clearly see the free energy of the liquid phase is minimum at all composition from pure A to pure B. Shape of the free energy curve remains same, that is inverse parabolic. It does not change, and I told you why it should not change, because this is depends on entropy and enthalpy, and both of them are functions of the xb square. So that is why they looks like a parabola. So that is very clear. So that, but the message is that whenever you are drawing free energy composition diagram in a particular phase diagram, you need to draw the free energy diagrams for all the phases, whether at a temperature T1 only liquid phase is stable or not, that does not matter. What is important is to show you the relative positions of these free energy curves. That is very important. So let us now do it at TA. So at TA, as you can see, I have already done it for your isomorphous system. At TA, what is going to happen? At TA, you can see here only at temperature A, temperature at A end, the that is compositions xp equal to 0 at the pure A end, the liquidus of alpha and liquid solidus of alpha meets. So that means what? The free energy curve of liquid and alpha will meet only at pure A end, others it will remain same. So again I draw liquid. So as I told you, only at A end liquidus of alpha and liquid will, sorry, G and free energy of alpha and liquid will touch. That is what you see here, it is touch, and beta will remain higher. Okay, that is how it will look like, very simple. And these diagrams actually are shown or obtained from this by looking at a phase diagram. That is why it is very easy to understand. Now I will do it at temperature T2, which is also very easy. Temperature equal to T2, this is A, this is B, xp. So at T2 you can see this is the most complex situations. At T2 there is a composition range in which pure alpha is stable, there is a composition range with alpha and liquid is stable, and there is a composition range in which liquid is stable. So there are 3, 1, 2 and 3 domains. So one is pure alpha, alpha plus liquid and liquid. So how to do that? Whenever you have a two phase field, I told you that both free energy curves will cross over each other. So that means free energy curve alpha and liquid will cross over each other. So how would I do it? Okay, first let me draw free energy curve of the liquid, and alpha, obviously because alpha is stable at the pure end, so alpha will be coming down. Sorry, this has to be drawn dotted line, otherwise you will be getting confused. Okay, let us draw it. So this is G alpha, and beta is not stable at all, so beta will be coming much above because beta is not present here. So this is G beta. So because these two free energy between alpha and liquid are crossing each other, the real stability will be obtained by drawing a common tangent between these two. So let me just draw a common tangent like this. So if I draw a common tangent, it will cross, it will cut the liquid curve here and the alpha curve there. Okay. So that clearly tells me very simply that this is the stability zone of alpha, this is stability zone of liquid. Okay, this is stability zone of alpha plus liquid. That is what you see in the phase diagram. Alpha is stable here for the small composition zone from here to there, okay, from here to there, and then alpha plus liquid and then liquid. So one thing you understood, whenever you have a two phase field and tie line at temperature T2 passing through the two phase field, these two free energy curves will cross over each other, and that must be done, otherwise you cannot have the condition that chemical potential at both the pure A and pure B ends satisfy the things. So anyway, let us do at temperature equal to eutectic temperature. At eutectic temperature, at equal to TE, this is the classic temperature at which things are different and distinct. What will happen? At eutectic temperature, 3 phases liquid and 2 solid phases are at equilibrium. So that only is possible, okay, only when you have common tangent between all the three curves drawn at a temperature at a composition and equal to composition given by these phase diagrams. So let us draw it. So let me first because at new temperature you can see here till this composition, this point from this to this, the solid alpha is stable, from this to this solid beta is stable, only in this part these three phases are at equilibrium. So let me just draw solid alpha curve, okay, and then I draw the liquid crossover. Liquid will be like this, and then I draw the beta. Okay, let me just put it, this is alpha, this is liquid, beta will be okay, this is beta. So you can clearly see, although I have not been able to do properly, these three curves are common tangent each other, okay, and these 2 points which you see here, alpha plus liquid beta, these two regions, this is pure alpha, alpha is stable, lowest free energy, this is beta has the lowest free energy, in between three of them are at common tangent. So therefore this will be region of alpha plus beta plus liquid, okay, that is what it is. Here alpha, beta, liquid, three phases are coexisting, so that is why you can see there is a composition domain, this is stable, and this point here I can mark it A, this is A, okay, A, this is B, so this is B on the phase diagram. That is how it is done. So therefore at a temperature TE all the three curves will be sitting in such a way that there is, you can draw a common tangent between them. So at T3 at T3 it is not difficult, much easy. At T3 liquid is not stable at all, at T3 is at this temperature only alpha and beta are stable, but there is a two phase field alpha plus beta, therefore alpha and beta the free energy curves will cross over. So liquid will be above GL, then alpha, okay, and then beta is different, okay. So you can clearly see that alpha and beta are crossing over, so there is a common tangent I can draw here between them. So this is what is, this is alpha plus beta, and this is beta. Remember this is G beta, this is G alpha free energy curves. So you can always draw a common tangent between alpha and beta free energy curves, and then you can show that the common tangent actually demarcates the regions to be two phase region between the two single phase regions alpha and beta, okay. So that is how actually the free energy composition diagrams for the utility systems are drawn, and I have shown you very clearly that this is very important in the perspectives of understanding the phase diagrams, and you can do it for other systems also. So let me just go back and start discussing about aluminum silicon alloy, what will happen. And I told you that aluminum silicon is a very important alloy system, and this phase diagram is shown here, you can clearly see. It is a classical phase diagram in the sense that there is a eutectic point here, this is the eutectic point, a temperature, and composition is given by this. It is about 11.8% of silicon, and temperature is about 573 degrees Celsius, and importantly you have a single phase zone here alpha, which is solution of silicon and aluminum, but on the right side silicon inside there is no such thing, it is a pure silicon. So now I know that the alloys which are important for industrial applications are the hypo-eutectic alloys, alloys which has compositions less than eutectic. Hyper ones are not very interesting because it contains hard silicon particles that makes the alloy very brittle, not used. So the next slide This is the classical aluminum silicon alloy microstructure I have shown you already. It contains continuous white aluminum matrix like thing, but it is not a matrix, it is basically aluminum phase, and then you have needle like silicon. Now as I told you, silicon is very brittle. If I take a silicon piece and just drop it on the floor, it will break or shatter into pieces. And so therefore these needles are basically makes the alloy brittle, not so good. So we need to modify this microstructure, and this is very important in the sense that you need a good machinability, good toughness and ductility of the alloy when you are using it as an engine block for many of the car engines. So what is done, and this is serendipity in the metallurgy or materials engineering, is that you add very small amount of sodium, strontium or earth, and amount is very small, it is about 0.1%. So that means if you use about 100 grams of the aluminum silicon alloy, you need about 0.1 gram of sodium or strontium. Sodium is Na, strontium is Sr, or rare earth metals or mixture of rare earth metals, sometimes it is known as Misch metal, M-I-S-C-H, Misch metal. 1, 2, 3. 3 different types of things are added, or sometimes together, sometimes separately, to modify the microstructure, to modify these silicon needles. And this has been discovered out of serendipity. Nobody knew that it will happen. Somebody probably had tried to add sodium into it and then found that microstructure do gets changed. What is the change you see? Okay, change you see is this. You can clearly see the earlier picture. This is 10 micrometer scale, and the needles are, silicon needles are very big and quite thick also. On the other hand, if you add about 0.1% silicon, the silicon needles become very fine, very fine silicon needles become. Not only that, you also find some amount of aluminum, which is alpha aluminum, which is present in the microstructure. It is shown at a high magnification view here. You can see the micron bar is 5 micron now. So you can modify the silicon needles, or eutectic rather, very fine scale, and as you know, if you make something very finer scale, your ductility and strength both improves. So by making this is finer, we improve the ductility, we improve the toughness, at the same time we do not change strength much. So this is what you want, this is what the industry people want. They want a wonderful material which will be used for many applications, and that is what you see here. But you know, the important part is this. In all this microstructure you see presence of alpha aluminum dendrites. So that means what? That means this alloy is not behaving like a eutectic alloy, it has become a hypo-eutectic alloy. So this particular phenomenon of modifying this eutectic microstructure, modification of eutectic microstructure from a coarse this microstructure like this to a fine ones like this is known as modification in the literature, and this is routinely done in the industry nowadays, and this can be explained using free energy composition diagram again, but I will not go into that details, but let me tell you what actually happens. If you add sodium, or if you add some amount of strontium or whatever it is, sodium, strontium or any Misch metal or rare earth metals like that, they actually hinder the growth of silicon needles. Remember, silicon is a metalloid, it has its own growth problems. Unlike other metals like aluminum, copper, it cannot grow very nicely. It cannot grow nicely in the sense that when atoms actually jump and sit on the surfaces of silicon, they cannot get attached along any plane. They need to be attached along certain twin boundaries. And I am not going to get details into those, because those will lead to different discussions deviating from the actual syllabus of the course, but you can read. These are very interesting. So sodium actually poisons the growth of silicon needles. Sodium sits on the silicon needle and it has been observed that it poisons. Basically it does not poison that, it removes the phosphorus. Sodium, strontium, whatever is the elements, they scavenge out the phosphorus in the melt, and if they scavenge out the phosphorus in the melt, the silicon cannot nucleate very easily. So what is the scavenging out? What actually happens is that if I add sodium, strontium or some Misch metal into the melt, reacts with this phosphorus in the liquid which is present. And you may be thinking, where from the phosphorus come? Okay, that is a very good question. Phosphorus actually comes from the liquid itself, from the ore. Aluminum silicon alloys, whenever prepared, we add the commercial purity aluminum, and commercial purity aluminum will have lot of phosphorus into it, and this phosphorus actually react with the aluminum from aluminum phosphide, and on the aluminum phosphide silicon needles nucleate and grow and become very long. So therefore, if I add sodium or if I add strontium, and this sodium and strontium preferentially react with this phosphorus and remove the phosphorus from the liquid, so that aluminum phosphide cannot form. If the aluminum phosphide cannot form, the silicon cannot nucleate on aluminum phosphide. So therefore, the nucleation of silicon is prolongated, and this lead to very finer silicon needles in the microstructure. That is what you see, a very fine scale silicon needles or very fine scale structure. So that is how things happens. There are other theories also. In fact, to be frank, this is not completely understood in materials and metallurgical engineering, how actually things happen. The other theory is that in commercial purity aluminum, you can have iron as one of the impurity in aluminum alloys. And iron with aluminum and silicon can form iron aluminides, iron silicides actually, AlFeSi type of phase. And this AlFeSi type of phase then can prolongate or rather make the nucleation of silicon difficult, and that is why silicon becomes finer. Anyway, let us forget about iron, but let us only think about that in aluminum silicon alloy you have phosphorus present, and this phosphorus reacts with aluminum and form aluminum phosphide, and this aluminum phosphide helps in nucleation of silicon. That is why you have easy nucleation of silicon and it grows very fast. But whenever you add sodium or strontium or other metals, it reacts preferentially with phosphorus, removes the phosphorus from the melt, so that aluminum phosphide cannot be formed, and because of the silicon nucleation is difficult, and when silicon is very difficult to nucleate, then it will not grow large, it remain finer scale, and that is how thing happens. This can be explained very easily using the phase diagram data. Let me just go back, let me see whether I have in here. Okay, I do not have. So let me just go back and explain it using the phase diagram. So what does it mean is that if I have a problem in nucleation of silicon in the liquid, so what it will do? It will basically lead to more undercooling. Okay. So that means if I have a aluminum silicon phase diagram like this is aluminum, silicon, pure, correct, sorry, this will be up. Okay, this is silicon has a much higher melting temperature. So this is silicon, this is XSi or mole fraction of silicon, this is aluminum, this is temperature, this is liquid, this is alpha aluminum plus silicon, this is liquid plus silicon, this is alpha aluminum, and this will be alpha aluminum phase split. This is what the phase diagram looks like. Now the moment you add silicon, and this composition actually sits at 11.8, okay, let me just remove this, let us write weight percent of silicon, 11.8 weight percent of silicon, and this temperature is something like 573 degrees Celsius, okay, sorry, 577 degrees Celsius, not 73. I hope you can see it carefully, 576 degrees Celsius. This is the eutectic temperature, eutectic composition. Now whenever I add sodium or strontium or some other metals to modify it, then what does it mean is that the eutectic temperature and composition shifts to higher. Composition shifts to higher, it becomes actually 14%. So this is 11, original one 11.8, and this one is 14 atom percent, weight percent, and this temperature is 555 degrees Celsius. So that means what? If you make the silicon nucleation difficult, it requires further 22 degrees of undercooling. Difference between 577 and 555 is 22 degrees. So this is, and this leads to change the eutectic composition to 14 atom percent. So therefore the eutectic alloy, which was originally eutectic alloy, now has become a hypo-eutectic alloy. Is it clear? It becomes a hypo-eutectic alloy, and because of this hypo-eutectic nature, it forms alpha aluminum dendrites in the liquid. That is why you see alpha aluminum dendrites in the microstructure, which I have shown you. So basically what it boils down is that, in a short way, that if you add sodium, strontium or something, it basically makes the growth or nucleation and growth of silicon difficult. Basically growth of silicon makes it difficult, and that is why you need more undercooling, because you need to provide more energy to the system, and then it has become a this same alloy which was eutectic alloy for aluminum silicon, when you add sodium it becomes hypo-eutectic alloy, and you get to see some lot of aluminum dendrites. And as you know, aluminum actually very soft metal, so therefore aluminum dendrites will make this alloy soft, ductile and tough. At the same time, as the eutectic has become finer, it will also lead to high strength and high ductility and toughness. That is how actually one can explain the modification of eutectic alloys. Okay, with this I will stop the discussion of eutectic. In the next class I am going to discuss about peritectic reactions and move over.